In this video, I'm going to talk about a few different behaviors and phenomenon that happen on the surface of the sun. So one of them that I'm going to touch on briefly is something you may have heard of, called a solar flare. A solar flare is when a certain portion of the sun's surface suddenly becomes a lot brighter for some period of time for no apparent reason. The reason is some kind of magnetic thing happens. The sun has as I've said before, very powerful, very dynamic, and always changing magnetic field. And so in some area, some kind of crazy magnetic thing happens, introduces a bunch of energy, makes that area of the sun brighter because of all the extra energy that it's gotten. Something like that. There's not a whole lot to solar flares. Another thing that you may have heard of are solar winds. So here's how the solar wind works. Out in the outer areas of the sun, maybe in the photosphere, especially in the corona and the outer layers like that, that gas can get a lot of energy, right? It can get very energetic, and sometimes some gas will get energetic enough that it is able to escape the sun's gravity. It can reach escape velocity and fly off into space. And that's solar winds. Solar winds are miscellaneous sun particles that have escaped the sun's gravity. They're very electrically charged, and they fly off into space. You may recall from my solar systems lecture that we think solar winds stripping Mars's atmosphere. We think that Mars used to have a much thicker, more Earth-like atmosphere, but that solar winds stripped it over time and into the very thin atmosphere Mars has now. And we think that the reason that hasn't happened to Earth is because Earth has a big, strong magnetic field that can exert a force on, well, it's not like Earth's magnetic field is strong for its size. It's maybe not that big and strong relative to other things, but anyway. It can exert a force on those solar wind particles, which are always charged, right? And it kind of redirects them to hit us at the poles, the North and South Pole. That's what causes the auroras. But that makes it to where it doesn't strip very much of the atmosphere off. We think Mars used to have a magnetic field, but it lost its magnetic field because it cooled down, and its molten metal core cooled and solidified, so it can't rotate anymore. And the core rotating and spinning, because it's like a fluid and it can do that, is the reason that we have a magnetic field. So we think that Mars lost its magnetic field because it cooled off, and then it didn't have a magnetic field to protect its atmosphere from solar winds anymore. Now, solar winds are happening all the time, right? It's basically like a constant process that material is escaping from the sun and flying off. So, yeah. Another related concept to solar winds are coronal mass ejections. If you've ever seen a documentary on the Science Channel or National Geographic or something about the sun, I'd say there's a pretty good chance that they had some kind of a cool CG visualization of a big loop of super energetic looking sun material forming and then bursting, and a huge cloud dramatically flies off of the sun. And yeah, that's the deal with coronal. That's a coronal mass ejection. a big magnetic event happens, which causes a large amount of mass to get ejected from the corona at once. Now, I think it can be easy to confuse coronal mass ejections and solar winds, because they're both like, you know, sun material getting shot off into space. And they are similar, but they aren't the same thing, because solar winds are kind of a lower level thing that's happening constantly. And coronal mass ejections are a rarer, not super rare, but pretty rare, and more dramatic thing than solar winds. So they're similar, but not quite the same. The last thing I'm going to talk about are sunspots. Sunspots are a feature of the sun that you may have seen in like pictures of the sun. They're just like these little dark, kind of tiley looking dark spots on the sun's surface. What are they? Why do they form? I'm going to talk about it. So the thing about sunspots is they're dark because they're emitting a lot less light than most of the sun's surface. They're still emitting a lot of light, to be clear. It's just way, way less than is normal for the sun. They're also a lot cooler than the rest of the sun. And again, to be clear, they are extremely hot, but just a lot less extremely hot than the rest of the sun's surface. And that's what causes them to be, you know, dark. But why is this? Why is it that sunspots form in this way? Well, to explain that, here I have like a little bit of the surface of the sun. So here we have a bunch of gas, right? And if you recall, this is like part of the photosphere. And if you recall, the photosphere is part of the convective zone. So we have some convection going on here. Here is a little cloud of gas. It's close to the top, right? So it has a pretty easy time of emitting its energy out into space. It's pretty cool. Down here, further down, we have another cloud of gas. It's closer to the center of the sun. It's hotter. It can't release energy as easily. So this cloud of gas has a much lower density, very significantly lower density than this cloud of gas. And so they're going to want to switch places. They're going to want to undergo convection, like I described last video. Now in the last video, I described it using arrows that kind of looked like this, sort of like a little recycling sort of looking arrow system. But that was a little bit misleading. Easy to draw and easy to understand, but a little bit incorrect. I'll explain more accurately what happens now, because it's important now. So what really happens, it's not that this whole cloud like moves down this way and this cloud moves up this way. The way it more happens is that this cloud goes directly up, right, like a straight line, basically. And this cloud up here kind of makes way for this cloud, not by moving entirely in one direction going down, but by kind of splitting up into smaller clouds. And each of the little subparts goes to the side in a different direction and then down. I hope that you can understand kind of what I'm trying to depict with this drawing here. But that's kind of what's going on here. And this is important for reasons I'll get to shortly. Now, let's suppose, and again, this is part of the surface of the sun. I don't know why I said that. That was not very... Anyway, like I said earlier, the sun has a very powerful magnetic field. So let's imagine that a big magnetic field line forms, and it comes up like through the surface of the photosphere. It's kind of forming you can see it's kind of forming a right angle with the surface, which is important. And when I say this is like, there are a variety of, this is kind of like a big bundle of smaller magnetic field lines. We can think of it as being like one field line for simplicity. Now here's the deal with magnetic field lines. The way magnetic fields work is that they exert a force which opposes motion that's at a right angle to the field lines. If you're trying to move along the magnetic field lines, that's fine. The force will actually support you if you're moving along a magnetic field line and you're charged, so you're affected by magnetism, right? But if you try to move at a right angle to a magnetic field line, it's going to apply a force to you which opposes that motion. It makes it harder to move at right angles to magnetic field lines. So one of the consequences of this is that when we have this big strong magnetic field line, right, that's going up and down like this, let's imagine we have two more gas clouds in kind of the same situation as here. Here we have a cooler one that's towards the top and a warmer one that's towards the bottom. Now this warmer one is going to keep on moving straight up like normal. It's hotter, it's less dense, it wants to move up. You know, it's floating. And this cooler one up here, it also wants to do this same thing that it would do normally. But it can't. The reason it can't is that when it tries to split up and go to the side and then down to make way for this, it can't go to the side, because this big strong magnetic field line is going to oppose its attempts to move to the side to get out of the way and make room for this hotter gas cloud underneath. So if it can't move to the side, it can't go down. Essentially, this magnetic field line is holding the cool cloud of gas at the top of the sun. And this, while it's doing that, the cloud of gas at the top is continuing to get rid of its energy. It's continuing to radiate light and energy out into space. Normally, you know, this gas cloud would only get to radiate off so much energy before it got cool and dense enough to sink down and another warmer gas cloud came up from under it. But here, this gas cloud that's being prevented from moving to the side is able to radiate off energy for way longer than it normally would. And so that causes a sunspot, you know, where the gas is way colder and darker than it normally would be. That's again because it's just had way more time to radiate that energy off than parts of the surface of the sun would ever normally have because of this big powerful magnetic field line. Now another important thing is, the sun makes a lot of magnetic field lines, right? But it makes magnetic field lines in all kinds of different angles. What if it made a magnetic field line that was kind of like this? It's kind of coming out of the sun like this. This magnetic field line might be as strong as this one, but this one maybe would not make a sunspot. Because if you recall, magnetic field lines oppose motion that goes at right angles to them. But here, if you had a warm gas cloud right here, since this one isn't making like very much of a right angle with the surface, this one, even if it's just as strong as this magnetic field line, it might not really be doing very much to keep the gas from moving out of the way. So this magnetic field line maybe would not actually create a sunspot. Alright. I think that about covers it for this video.